welcome to our first lesson with Math for Elementary Ed 2, or Math 278. Each week we will cover one particular cluster of standards for each grade level. We're covering grades 6, 7, and 8. So this week we're covering the first set, which is ratios and proportional relationships. Here are the different individual standards with which that we have to cover. I've tried to cover each piece of these, a couple of examples from each number and subletter. So I hope that I've covered everything and you feel comfortable with the material as well as using manipulatives with the material. A bread recipe calls for 5 cups of flour and 2 teaspoons of yeast. How much flour and how much yeast do you need for 2 batches of bread? Draw a picture that shows the batches as well as the total amount of yeast needed. Okay, so for batch 1, we need 5 cups of flour and 2 teaspoons of yeast. So I drew a picture of 5 cups with 2 teaspoons. If I have another batch, I would need another 5 cups and another 2 teaspoons of yeast to go with it, for a total of 10 cups of flour and 4 teaspoons of yeast. How many batches can you make with 15 cups of flour and 6 teaspoons of yeast? Indicate the batches in the picture. So I went ahead and I grouped the first 5 cups of flour with the first 2 teaspoons of yeast. So there is one batch. I went 5 more cups of flour and 2 more teaspoons of yeast for a second batch. And it looks like I have enough at the end there to create a third batch. We say that the ratios 5 to 2, 10 to 4, and 15 to 6 are equivalent. In this case, even though the amounts of each ingredient are not the same, they would make the same kind of bread. Find another ratio equivalent to these and that would correspond to the same kind of bread, and draw a picture to represent it. We could quadruple the recipe, meaning I would have 4 batches, so I would need 20 cups of flour and I would need 8 teaspoons of yeast. Another recipe calls for 2 cups of flour and 1 teaspoon of yeast. How much flour and how much yeast do you need for 2 batches of this bread? Batch 1, we need 2 cups of flour and 1 teaspoon of yeast. Batch 2, we have 2 cups of flour and 1 teaspoon of yeast, for a total of 4 cups of flour and 2 teaspoons of yeast. Compare this bread with the one batch from our very first recipe, which is the top line of here. Do you think these ratios are equivalent? No, these ratios are not equivalent because the amount of flour is different when the amount of yeast stays the same. An animal habitat includes 3 snakes, 2 alligators, and 5 lizards. What are the 3 ratios you can use to describe the relationships between these animals? We're going to use Cuisenaire rods to represent the number of each animal type. So I went to our interactive Cuisenaire rods, which is located again in the manipulative folder. I let the green one represent the snake. As you can see, it's 3 units long. The alligator is 2 units long, and the lizard is 1, 2, 3, 4, 5 units long. And I let the orange rod be the total number of animals there are, so there's 10 of them. Compare the total number of animals to the number of snakes. So the total number of animals is 10 and the number of snakes is 3. I can see that this is 10 semicolon 3, 10 to 3, or 10 divided by 3. This is whole to part, so we're comparing the whole number of animals to a part of the animal, so a piece of it. Compare the lizards to the animals. So the lizards is the yellow one, and I put that on top of the total number of animals. This is a 5 to 10 ratio using semicolons, the word to, and a fraction. Now we're comparing a part to the whole. Compare lizards to alligators, alligators to snakes, and snakes to lizards. Express each in 3 ways. What do these ratios compare? Okay, using the interactive Cuisenaire rods, again, this link is in the manipulative folder at the top of our page. It's asking us to compare lizards to alligators. So I just pulled out some Cuisenaire rods here. So this represents our lizard, and the alligator is represented by the red one. So this can be written as a 5 to 2 ratio. It further asks us to do alligators to snakes. So I need another red one to represent the alligator. And then the green one is our snake. So alligator to snake is a 2 to 3 ratio. And then snakes to lizards. So I need another snake, which is the green one. Oops. And then the lizard, which is the yellow one. I shouldn't connect them like that. Okay, so then this one would be a 3 to 5 ratio. Notice that none of these 3 ratios compare with the whole. Therefore, these are called part-to-part ratios. Part-to-part ratios because they compare different pieces of the total, but not the total itself. On the cross-country team, there are 2 boys for every girl. We would say this is a 2 to 1 ratio, also written as 2 semicolon 1, or 2 boys over 1 girl, or 1 girl over 2 boys. Order doesn't particularly matter. So again, part to part would be boys to girls 2 to 1, or girls to boys 1 to 2, versus part to whole, boys to total. There are 3 total people on the cross-country team. So boys would be 2 to 3, and girls would be 1 to 3. At a birthday party, there are 3 purple balloons for every 2 blue balloons. So in the bottom right-hand corner, I have the balloons there for us. So part to part, we can compare purple to blue or blue to purple. So purple to blue is 3 to 2, and blue to purple is 2 to 3. Or we could compare part to whole. We could compare the purple to the total balloons and the blue to the total balloons. So purple, there are 3 of them, 3 to 5, and blue, 2 to 5. We can express a situation using multiple representations of a ratio, such as the following. Complete the table about Jack's birthday party. There are 3 chocolate cupcakes for every 1 vanilla cupcake. Pause the video, fill in the table, and let's see if we can't come together at the end here. Okay, so chocolate cupcakes to vanilla cupcakes. So for every 3 chocolate, there are 1 vanilla, so 3 to 1. Vanilla to chocolate cookies or cupcakes is 1 to 3, the exact opposite. Now the last 2 are talking about the total number of cupcakes. So 3 plus 1 is 4. So chocolate cupcakes to the total is 3 to 4, and vanilla to the total is 1 to 4. Using the semicolon, our numbers stay in the same location just with the semicolon. And in fraction form, the numbers stay the same. We use them in fractions. Here are some questions. Hippos sometimes get to eat pumpkins as a special treat. If 3 hippos eat 5 pumpkins, how many pumpkins per hippo is that? Well, we're comparing pumpkins to hippos. Well, 5 to 3 is the ratio. Therefore, each particular hippo will get 5/3 of a pumpkin. Or we could say each hippo gets 1 2/3 of a pumpkin. Lindy made 24 jelly bread sandwiches with a 16-ounce jar of jelly. How many ounces of jelly per sandwich is that? So here we are determining ounces to sandwich. So jelly to sandwich is 16, and we made 24 sandwiches. We could reduce or simplify such that each sandwich will get 2/3 of an ounce of jelly. Jake bought 350 rolls of toilet paper for the whole year. How many rolls of toilet paper per month is that? So we're comparing rolls of toilet paper to the month. There are 350 rolls of toilet paper. If we divide that by 12, because there are 12 months in 1 year, that means that each month there will be 29 1/6 roll of toilet paper. In the world's longest running experiment, scientists have tried to capture tar pitch dripping on camera. In the past 86 years, 9 drops have formed. How many years per drop is that? So we're comparing years over drops. So in 86 years, there were 9 drops. 9 5/9, there is 1 drop for every 9 5/9 year. Imagine that 12 goats got into a dumpster behind a pizza parlor and ate 3 pizzas. How many goats per pizza would that be? So we are comparing goats to pizza. There are 12 goats and 3 pizzas. When I divide, we get 4, which means there are 4 goats per pizza. In a gumball machine, the ratio of green to yellow gumballs is 2 to 1. If there are 6 green gumballs, how many yellow are there? So here are 2 green gumballs and 1 yellow gumball, but we need 6 of them. So I build another set. Now I have 4 green and 2 yellow, but we still need to get to 6. So 6 green and 3 yellows. 2 to 1 is equivalent to 6 to 3. The ratio of incorrect answers Ashley got on a math quiz is 3 to 7. If she missed 9 questions, how many questions did she get correct? So I know that there are 3 wrong for every 7 that she gets correct, but she missed 9 questions. So we need to build enough 9 X's to see how many questions she got right. So if I add another set, that would mean I have 6 missed questions, and I would then have 14 correct. Not enough yet, so I add another set. Now I have 9 questions incorrect, and I have 7, 14, 21 correct answers. We could also use a table to help build this. The questions missed are 3, and the questions correct are 7. We wanted to know how many questions we got correct, and we discovered through using pictures that it was 21. I also know that 3 times 3 gives us 9. Also, 3 times 7 gives me 21. So they are the same when we multiply. In order to draw an accurate model of a skyscraper, an architect needs to draw the length and the height using the ratio 1 inch on paper to 1,000 feet in real life. If the height of the building is 2,100 feet, how many inches will the architect draw on paper to show the height? Some information that we know. We know that the paper versus real model has a 1 to 1,000 ratio. We also know that our real building is 2,100 feet. Well, I don't quite know what I need to multiply 1,000 by to get 2,100. But I do know that if I were to take 1 times 1,000, I would get my bottom number. Therefore, I could ask myself, what times 1,000 would give me 2,100? Well, we know according to our place value chart that that would be 21. The ratio of green candies to pink candies is 6 to 8. Write two equivalent ratios, one with a total of 42 candies and one with a total of 7 candies. I know that there are 6 green to 8 pink for a total of 14. We're particularly interested right now in 42 candies for a total. So we ask ourselves, what times 14 will give us 42? Well, that would be 3. So then we can take each other number and multiply by 3 as well, so that we get an equivalent ratio. 6 times 3 is 18, and 8 times 3 is 24. We have created one equivalent ratio. We also want to know what we could multiply by to get to 7. Well, to get from 14 to 7, yes, we could subtract 7, but we also could divide by 2. So if I were to divide the other numbers by 2, we would get 3 and 4. There are many equivalent ratios that we can make. And we can simplify equivalent ratios using visual models, tables, and fractions. Help the teachers decide if they have enough students for at least 15 basketball teams with 5 players per team. Will there be students who do not get to participate? Here are the following things that we know. Mr. Jones's class has the same number of students as Mrs. Gilmore. Their female to male ratio is 1 to 2. Mr. Jack's class has a female to male ratio of 5 to 4, and they have 12 boys. Mrs. Gilmore's class has a female to male ratio of 3 to 2 with 18 girls. Let's start with Mr. Jack's class. He has a female to male student ratio of 5 to 4 in his class. He has also 12 boys. Well, how can we then determine how many girls there are? Let's build a table. We know that there are 5 girls for every 4 boys. If we have 12 boys then, how many girls are there? Well, 4 times 3 gives us 12. Therefore, 5 times 3 is 15. Now we can find out how many total students we have by adding 15 girls plus 12 boys for 27 students. Let's go visit Mrs. Gilmore's class. She also has a female to male student ratio of 3 girls to 2 boys. If her class has 18 girls, how many boys are there? So we have a 3 to 2 ratio. We know this time that we have 18 girls, so I can build to 18 by multiplying 3 times 6. So therefore, 2 times 6 gives us 12. Her class has a total of 18 plus 12, so 30 students. Mr. Jones's class has the same number of students as Mrs. Gilmore's class. His class has a female to male ratio of 1 to 2. So if we have a female to male ratio of 1 to 2, this particular ratio has a total of 3. If they have the same amount of students as Mrs. Gilmore's class, that means the total also has to be 30. I can get from 3 to 30 by multiplying by 10. If I multiply 1 by 10 and 2 by 10, we get 10 and 20 respectively. Therefore, we also have 30 students here. We did not have to fill out the table, but it was good practice anyways. We need to know how many total students we have. So if I add all my students up, we have a total of 87 students. We also know that one team is equal to 5 students. Let's use a double bar line to determine how many teams we can make with the students that we have. One team is 5 students. 2 teams is 10 students. And if we were to fill out our whole table, we'd get to 9. We don't have enough room to continue because we need to get to 87. Our table only went to 45. So I continued with a second table and just kept on going. 10 teams is 50 students, 11 is 55. I get all the way to 17 teams and I have 85 students. I don't have enough to have 18 teams. That would require 90 students. So I have 87 students altogether and a team to make 85. That means that 2 students won't get to play. Rory and Lorelei are racing snails in science class together to gather data about habitat. Here is the data they collected. Snail A went 5 inches in 10 minutes, and snail B went 3 inches in 20 minutes. Rory says snail B can travel 23 inches in 40 minutes. Snail B will win. However, Lorelei says snail A can travel 20 inches in 40 minutes. What might Lorelei's reaction be to Rory, and which snail will actually win the race? Let's look at snail A first. Its ratio is 5 inches to 10 minutes. We're particularly interested in both situations, how far they can travel in 40 minutes. Well, 10 times 4 gives me 40, so 4 times 5 is 20. So snail A can travel 20 inches in 40 minutes. Let's compare that to snail B. That snail can go 3 inches in 20 minutes, and we're also particularly interested in how far they can go in 40 minutes. So 20 times 2 is 40, and 3 times 2 is 6. Remember, a ratio is a comparison by division. We need to use their multiplicative relationships. When we compare how far each snail will travel in 40 minutes, we see that snail A travels much farther in 40 minutes than snail B. Therefore, snail A wins the race. Now there are 3 snails. Which of these 3 snails will go furthest in 1 hour? So I've got some charts for us that we can fill out. Chart 1, we know that this snail travels 5 inches in 10 minutes. We want to know how far they can go in 1 hour. Recall that 1 hour is equal to 60 minutes. So I can get from 10 to 60 by multiplying by 6. 5 times 6 gives us 30. Snail B can crawl 3 inches in 20 minutes. We're again particularly interested how far they can go in 60 minutes or 1 hour. 20 times 3 gives me 60. So 3 times 3 gives us 9. So far, snail A is truly winning. Snail C. Snail C can go 8 inches in 15 minutes. Again, we want to know how far they can go in 60 minutes. 15 times 4 gives me 60, so 8 times 4 is 32. It appears as if snail C will win the race. Ashley spent 40 minutes on homework and Michael worked for 1,800 seconds. Michael said, "Wow, I spent longer on my homework than you." Ashley said, "I'm not sure about that. Do you agree with Michael's statement and explain?" We know that 1 minute is 60 seconds, so we can create a double bar line with minutes comparing to seconds. So 0 minutes would be 0 seconds, 1 minute is 60 seconds, and I go all the way over to 6 minutes and 360 seconds. We have a long way to go. So we're going to create another chart, and I'm going to base it off of 5 minutes at a time so that we can get going on our chart a little more quickly. So still 0, 0, 5 minutes is 300, 10 is 600, 15 is 900, etc. And then I circled 30 minutes in 1,800 seconds and 40 minutes with 2,400 seconds. Clearly, 40 minutes is longer than 1,800 seconds. So Ashley spent more time on her homework.